In the vast silence beyond the outermost boundary of our planetary neighborhood, something ancient drifts without warning. It emits no light. It casts no shadow. Yet its presence is written in the trembling of space itself. Tonight, we visualize a cosmic intruder, a rogue black hole, wandering through the darkness until it encounters our solar system. From a state-of-the-art observation ring built by NASA and its global partners, scientists watch gravitational sensors spike beyond anything ever recorded. Imagine standing on a platform suspended above the stars as distant planets begin to shift from their predictable dance. The mathematics of centuries collapses in seconds. Instruments scream warnings while data streams paint a terrifying picture. Space itself is bending toward an invisible abyss. But the true horror is scale. This object is not hunting us. It is simply passing through. And that alone may be enough to destroy everything we know. What happens when gravity stops being a force and becomes a predator? The answer begins at the frozen edge of our solar system, where the first world will feel the pull. And what scientists witness next will redefine the meaning of catastrophe. The first victim is distance itself. Objects billions of kilometers away begin drifting from their expected paths. In the outer solar system, frozen worlds that have orbited peacefully for billions of years experience a force they cannot resist. Their trajectories elongate, then twist, then accelerate. From the observation station, scientists watch simulation overlays collide with reality. A gas giant trembles as tidal forces stretch its atmosphere into luminous streams. Its rings fracture into glowing arcs, forming a spiraling ribbon of debris that curves toward an unseen center. This is not an explosion. It is slow disassembly. Gravity does not smash. It pulls patiently and absolutely. Sensors reveal something even more terrifying. The rogue black hole is not merely passing nearby. Its path intersects the plane of planetary orbits. That means every world will feel its influence in sequence. As researchers scramble to predict the order of destruction, they realize something chilling. Earth is not first, but it is not safe. And the next planet to be touched will demonstrate exactly what tidal gravity does to an entire world. What happens when a planet's own mass betrays it? The answer arrives with heat, motion, and unimaginable pressure. The next phase is heat, not from fire, but from motion itself. As the rogue black hole passes closer, gravitational tides knead a rocky planet like soft clay. Its crust fractures into continental plates that grind against one another at unimaginable speed. Mountains collapse. Volcanoes erupt simultaneously across the globe. But the most shocking transformation happens to oceans. As gravity stretches the planet, water does not remain level. Entire seas surge toward the direction of pull, forming towering walls of liquid thousands of kilometers high. Friction converts motion into heat. The oceans begin to boil. From orbit, the world glows with expanding clouds of steam. Atmospheric gases escape in luminous streams, torn away like threads. Scientists observing the event struggle to process the scale. This is planetary erosion in real time. Yet something even stranger appears on their instruments, a gravitational echo. The black hole is accelerating, slingshotting from its interaction with planetary mass. Each encounter increases its destructive reach. And now, calculations reveal a new trajectory. The next world in line is larger, richer in water, and far more fragile. If oceans can boil without fire, what happens when gravity touches a living planet? Across millions of kilometers, gravitational influence arrives before visual confirmation. Instruments detect distortion long before telescopes reveal the cause. Light from distant stars curves dramatically, sketching the invisible outline of the intruder. On the observation station, a quiet realization spreads. This event is not random chaos. It is a chain reaction governed by pure physics. Each planetary encounter feeds the black hole momentum, altering its path deeper into the solar system. Computer models update continuously, and one projection freezes every observer in silence. Earth lies within the corridor of closest approach. Not collision, but proximity. And proximity is enough. Scientists deploy probe drones toward the advancing distortion field. Their transmissions reveal particles accelerating, dust forming luminous streams, and space itself stretching into elongated filaments. This is gravity sculpting matter like an artist of destruction. But the most haunting data arrives last: time dilation signatures. Clocks aboard the probes begin to slow. The closer the black hole moves, the more reality itself warps. And if time can bend, survival may not depend on distance alone. What happens when our world enters a region where time and gravity refuse to behave? The answer is approaching faster than anyone predicted. Orbits once defined by elegant precision transform into spirals of uncertainty. A nearby planet's atmosphere ignites in aurora-like ribbons as charged particles accelerate through its magnetic field. The sky glows, then tears. From a station's panoramic viewport, scientists witness a phenomenon never observed in recorded history. A planet stretched into an elongated shape, its equator bulging while polar regions compress. Gravity is redistributing matter itself. But the most devastating transformation is yet to come. As tidal forces intensify, internal pressure rises. The planet's core shifts off-center. Rotational stability fails. The entire world begins to wobble, a slow, catastrophic loss of equilibrium. Data streams predict that Earth will experience similar tidal deformation if the black hole passes within a critical threshold. Continents would fracture. Atmosphere would escape. Oceans would surge skyward. And yet, one scientist notices something unexpected: a narrow corridor where gravitational stress is temporarily reduced. A possible observational window, or a fleeting chance to study the event from unprecedented proximity. The decision is made. The station will hold position. What they're about to witness next will not be theoretical. It will be personal. And the first visible sign will appear in Earth's sky. Earth's sky changes before anyone understands why. At first, it appears as a subtle distortion. Stars near the horizon stretch into delicate arcs, like reflections on rippling water. Then the moon's orbit shifts by a fraction of a degree. A fraction, but enough to trigger global alarm systems. From the observation station, mission specialists from the European Space Agency track the gravitational gradient in real time. Data confirms the unthinkable. The rogue black hole has entered the inner solar system's influence zone. It is not visible, but its presence is undeniable. Earth's oceans begin responding first. Tides rise far beyond any known prediction, not in cycles, but in a continuous surge toward a single direction in space. Coastal cities disappear beneath advancing walls of water. Yet there is no storm, no wind, only gravity pulling an entire planet out of balance. In orbit, satellites drift from stable paths. Some accelerate, others fall inward. Communication networks fracture into silence. But the most terrifying observation is yet to come. Instruments detect microscopic stretching within Earth's crust. The planet itself is beginning to deform. And if deformation has started, rupture cannot be far behind. Across Earth's surface, gravity no longer points straight down. Sensitive instruments record a measurable tilt in the direction of pull. To the human body, the shift is subtle, a faint sense of imbalance. But to oceans, atmosphere, and tectonic plates, it is catastrophic. The Pacific Ocean rises first, forming a colossal migrating bulge that crawls across the planet like a living entity. Entire ecosystems are displaced within hours. As water mass redistributes, pressure along fault lines multiplies. Earthquakes erupt in synchronized chains across continents. From the orbital observation ring operated by the European Space Agency, scientists witness an unprecedented sight: Earth's atmosphere stretching into a glowing stream extending thousands of kilometers into space. It resembles a comet tail, but the comet is our planet. Spectral analysis shows oxygen and nitrogen escaping at accelerating velocity. The protective blanket of life is unraveling. Yet amid the destruction, the sun's light bends dramatically around an unseen point in space. For the first time, the rogue black hole's position becomes visible through pure distortion, and its path is closer than any model predicted. The moon becomes the next casualty. Once Earth's steady companion, it now drifts from its orbit like a ship losing anchor. Gravitational tug-of-war begins between Earth and the rogue intruder. From a station's panoramic observatory, astronomers witness the moon elongate under tidal stress. Its surface fractures in radial patterns, releasing plumes of dust that shimmer in sunlight. Entire craters collapse inward. Then comes the moment calculations predicted, but no one was prepared to see. The moon begins shedding material. Streams of rock and debris spiral away, forming a luminous arc across space. The consequences for Earth are immediate. Without lunar stabilization, Earth's rotation begins to wobble. Day and night cycles destabilize. Atmospheric currents spiral into violent turbulence. Yet one scientist notices a terrifying acceleration in data readings. The black hole is no longer merely passing through. It is interacting gravitationally with the sun itself. And when a star becomes part of the equation, the scale of destruction changes forever. At the heart of the solar system, the sun responds. Its immense mass resists distortion. But even a star cannot ignore proximity to a black hole. Solar plasma erupts into towering prominences thousands of times larger than Earth. Observers detect a subtle displacement of the sun's center of mass. This shift sends gravitational ripples outward, compounding the chaos already unfolding across planetary orbits. On Earth, skies blaze with continuous auroras visible even at the equator. Charged particles flood the atmosphere as the magnetic field strains under gravitational stress. But the most alarming discovery comes from timekeeping instruments aboard the station. Clocks nearest the distortion begin to lag measurably. Time dilation has become observable within the solar system itself. To witness cosmic catastrophe is terrifying. To witness reality itself slowing is something far deeper. The black hole is now close enough that light paths around it intersect Earth's orbit. Soon, it will pass between Earth and the sun. When that alignment occurs, day may not become night. It may become something far stranger. The alignment begins with silence. Daylight dims not because the sun is blocked, but because light itself is redirected. The sky fractures into rings of distorted brightness. From orbit, Earth appears wrapped in a halo of warped sunlight. Shadows behave unpredictably. Some vanish entirely. Others stretch into impossible shapes. Scientists observing from the International Station operated jointly by NASA and global partners realize they are witnessing gravitational lensing on a planetary scale. The black hole has positioned itself between Earth and its star. Temperatures plunge across regions facing the distortion, while others experience sudden bursts of concentrated solar radiation. Climate systems collapse into chaos within minutes. Then comes the phenomenon never before seen in human history. A visible arc of the sun appearing duplicated around an invisible center. A ring of fire suspended in warped space. It is beautiful. It is terrifying. And it means the closest approach has begun. In the next moments, tidal forces will reach maximum intensity, and Earth will face the ultimate test of structural survival. Peak tidal stress arrives like a slow-motion catastrophe. Earth elongates by measurable kilometers along the axis facing the intruder. The planet does not shatter, it stretches. Deep beneath the surface, the mantle flows under impossible pressure. Volcanoes erupt in chains encircling the globe. Molten rock becomes visible from orbit as glowing veins across continents. Oceans surge upward into space-facing tides, so immense they partially detach from the surface, forming transient arcs of liquid suspended by gravity alone. The observation station records something astonishing: fragments of Earth's upper atmosphere accelerating into a continuous stream, feeding toward the black hole. The planet is losing mass in real time. Yet amid devastation, structural integrity holds, barely. Earth survives the moment of maximum pull. But survival is not safety, because the black hole has not yet passed. It is still approaching its closest gravitational interaction with Earth's orbit. And when it swings past, the release of tension will be just as violent as the pull. Then it happens, the swing by. The rogue black hole passes the point of closest approach and begins accelerating away, slingshotting from the sun's gravitational well. For a moment, the solar system exhales, but physics demands balance. The immense tension placed upon Earth's structure releases violently. Tectonic plates snap back toward equilibrium, generating shock waves that travel through the entire planet. Megaquakes ripple across continents. Oceans crash back into basins with unimaginable force. From orbit, debris clouds surround Earth, fragments of atmosphere, water vapor, and rock forming a temporary ring. Yet as scientists analyze trajectories, a new realization emerges. The black hole's departure path intersects another planetary orbit. The destruction is not over. It is moving deeper into the solar system's interior architecture. Earth has survived the encounter, but permanently changed. And as observers turn their instruments outward, they witness the next world beginning to unravel. As the rogue black hole departs Earth's orbit, the solar system does not return to calm. Instead, a delayed cascade begins. Orbital paths that once formed stable ellipses now wobble unpredictably. Planetary resonances amplify, turning subtle disturbances into accelerating deviations. From the observation station, scientists map the gravitational wake left behind. It is not empty space. It is a corridor of warped geometry where trajectories no longer behave normally. Dust, ice, and fragments of atmosphere drift along invisible currents like leaves in a cosmic river. Earth's newly formed debris ring glows faintly as sunlight scatters through vaporized oceans. The planet spins unevenly, its axis permanently shifted. Weather systems reorganize into colossal storm bands encircling the globe. But attention turns outward again. A nearby terrestrial planet enters the distortion corridor. Its orbit tightens, accelerating toward the sun before bending violently toward the departing black hole. Two massive gravitational forces now compete for dominance. The result will not be stability. It will be structural failure on a planetary scale. The solar system has become a laboratory of destruction, and the next transformation will reveal what happens when a world is stretched beyond its own gravity's ability to hold together. The competing gravitational forces reach equilibrium for only a heartbeat, and in that heartbeat, a planet tears. Observers witness the formation of a Roche limit event in real time. As the world approaches the boundary where tidal forces exceed self-gravity, its surface fractures into concentric bands. Mountain ranges collapse into flowing ridges. Oceans lift and separate into luminous ribbons of vapor. Then the planet begins to disassemble. Not explosively, but elegantly. Streams of rock spiral outward, forming a widening disk of debris around the path of the black hole. Each fragment follows a trajectory defined by pure mathematics and absolute force. The sun's light ignites the debris into a glowing halo visible across the inner solar system. On the station, silence dominates. This is planetary death by gravity alone. Yet instruments reveal something even more consequential. The redistribution of mass alters gravitational balance throughout the solar system. Every orbit shifts again. Earth's survival window narrows, because the next orbital perturbation will send a cascade of asteroids inward, and they're already on their way. The asteroid cascade begins as a distant shimmer, then resolves into a storm of motion. Millions of fragments, once stable in remote belts, now accelerate inward along intersecting paths. Earth's altered orbit intersects several of these trajectories. From orbit, the planet is encircled by streaks of incoming debris, each leaving incandescent trails as they encounter residual atmosphere. But most never reach the surface. Instead, they become trapped in chaotic orbital resonances, forming a temporary swarm around Earth. The planet now travels through a moving field of stone and ice. Within the observation station, scientists deploy autonomous probes into the swarm. Their data reveals gravitational turbulence, so intense that trajectories change moment by moment. Navigation becomes impossible. Then a new signal appears, subtle, rhythmic, unmistakable. Gravitational waves from the rogue black hole are interacting with the sun's own oscillations. The star itself is ringing like a bell struck by cosmic force. And when a star vibrates, the entire solar system must respond. Solar oscillations intensify into colossal waves rippling across the star's surface. These vibrations propagate outward as gravitational pulses, subtly compressing and expanding space throughout the system. Planets respond like buoys in an invisible ocean. Their orbits stretch and contract rhythmically. The effect is small, yet relentless. Earth's atmosphere, already thinned, shimmers with continuous auroral storms driven by solar instability. Radiation levels surge. The planet glows faintly even from deep space. But the observation station detects something unprecedented, a resonance pattern forming between the Sun, Earth, and the departing black hole. Three massive bodies locked in a temporary gravitational harmony. Such alignment cannot last. When resonance breaks, stored energy will release unpredictably. Simulations generate multiple outcomes. None show stability. One projection, however, reveals a possibility so extreme it forces immediate attention. A gravitational lensing event capable of magnifying distant galaxies across Earth's sky. If the geometry aligns perfectly, humanity may witness the universe moments before their world changes forever. The alignment reaches precision beyond probability. Light from distant galaxies bends through the gravitational geometry formed by Sun, Earth, and black hole. Earth's sky transforms into a panorama of magnified cosmic structures, spiraling galaxies, luminous arcs, and clusters normally invisible to the naked eye. The universe reveals itself in impossible clarity. For a brief interval, observers witness light that has traveled billions of years, arriving at the moment of planetary crisis. Yet the beauty carries danger. Concentrated radiation floods Earth's surface. Atmospheric loss accelerates as energetic particles escape into space. On the station, scientists understand the paradox. The same alignment revealing the cosmos is also destabilizing Earth's remaining atmosphere. Then resonance collapses. Space snaps back toward equilibrium. Light paths normalize. The cosmic display fades. But the energy released from that collapse propagates outward toward the black hole's path. And the interaction about to occur will alter the structure of the solar system permanently. The black hole's trajectory shifts once more, perturbed by the resonance collapse. Its path curves deeper into the solar system's architecture before finally bending outward. This final interaction triggers a redistribution of angular momentum among the planets. Orbital distances change permanently. Some worlds drift outward into colder regions. Others migrate inward toward the Sun. Earth's new orbit stabilizes farther from its original path. Days lengthen. Seasons transform. Yet the most dramatic effect occurs within the Sun itself. Gravitational stress alters internal plasma flow, creating asymmetrical brightness across its surface. Solar output fluctuates unpredictably. The solar system is no longer the system it once was. It has been reshaped, but one final encounter remains. As the black hole departs, it passes through a dense field of residual debris, fragments of worlds it destroyed. What happens when a black hole feeds on the remnants of planets within sight of those who survived? As the rogue black hole traverses the debris field, matter spirals inward, forming a luminous accretion disk. For the first time, the invisible intruder becomes visible through the glow of consumed material. Streams of vaporized rock emit intense radiation as they accelerate toward the event horizon. Light bends around the disk, creating a brilliant halo suspended in darkness. From the observation station, scientists witness a process typically hidden in distant galaxies, black hole feeding, occurring within their own celestial neighborhood. The spectacle radiates across the solar system, illuminating drifting debris clouds with eerie brilliance. But with feeding comes momentum. The black hole accelerates again, gaining velocity from consumed mass. Its escape trajectory is now confirmed. It will leave the solar system entirely. Yet departure does not mean reversal. The changes imposed on planetary orbits, stellar behavior, and Earth itself are irreversible. The visitor will vanish into interstellar darkness, leaving a transformed cosmic home behind. With its final gravitational influence diminishing, the rogue black hole recedes toward interstellar space. Instruments record declining distortion levels. The solar system begins a long process of stabilization. Orbital paths settle into new configurations. Debris clouds disperse into rings and belts. Earth rotates with a new axis, beneath a thinner atmosphere, encircled by remnants of oceans that once defined its surface. From orbit, scientists assess survivability. Despite catastrophic loss, the planet remains structurally intact. Gravity endures. The sun still shines. But a deeper realization emerges. The solar system has become evidence of cosmic vulnerability. Even stable systems can be reshaped by wandering forces beyond prediction. Yet within destruction lies knowledge. Every measurement gathered during the event expands understanding of gravity, time, and cosmic structure. Humanity has witnessed a phenomenon usually confined to distant galaxies, and what they learned will influence every future exploration of the universe. Recovery begins not on Earth's surface, but in orbit. The observation station becomes the center of analysis for a transformed solar system. Data archives contain unprecedented measurements of tidal forces, time dilation, and planetary deformation. These records will redefine astrophysics for generations. From orbit, Earth's surface reveals new geography, altered coastlines, exposed mantle regions, and vast atmospheric scars. Yet liquid water persists in isolated basins. This persistence becomes the focus of scientific hope. If gravity could not fully destroy Earth's structure, perhaps life can endure adaptation. Meanwhile, debris rings around Earth begin coalescing under mutual attraction. New natural satellites may form over centuries. The planet is evolving under new physical conditions, and humanity must decide whether to rebuild on a changed world or expand beyond it. Across the solar system, migration continues. Outer planets drift slightly inward. Inner worlds settle into wider orbits. The architecture of billions of years has been rewritten. Astronomers observe a newly formed asteroid belt composed of fragmented planetary remnants. Its composition provides direct insight into internal planetary structure. The sun's oscillations gradually diminish, though asymmetry in brightness remains. Solar cycles will follow new patterns never before observed. Earth's atmosphere stabilizes at a thinner equilibrium. Climate patterns reorganize into persistent megastorm systems encircling equatorial regions. Yet beneath these changes lies a profound scientific revelation. Gravitational encounters of this magnitude can reshape entire systems without total destruction. The solar system has survived transformation, but survival carries memory, written in orbital mechanics, planetary scars, and altered starlight. Long-term simulations reveal an unexpected outcome. The gravitational encounter has increased system stability in certain regions. Orbital resonances that once risked collision have been disrupted. Paradoxically, destruction has produced new balance. Scientists identify zones of enhanced habitability where radiation exposure and orbital stability align favorably. Exploration initiatives begin mapping these regions for future expansion. Earth, though altered, remains central to human history. Its survival becomes a symbol of resilience within cosmic uncertainty. Yet one question persists among observers. How common are such encounters across the universe? The answer may redefine our understanding of planetary system evolution itself. Analysis of recorded data reveals the rogue black hole's origin trajectory. It traveled for millions of years through interstellar space before encountering our system. Such wanderers may be more common than previously believed. Invisible travelers shaping galaxies through rare but transformative encounters. The solar system's experience becomes a case study in cosmic dynamics. Models of planetary formation must now include the influence of passing massive objects. For humanity, the lesson is profound. Stability is temporary. Motion is universal. Change is inevitable. But knowledge transforms fear into understanding. And understanding opens pathways to preparation. Future generations will watch the stars with new awareness, not only for beauty, but for movement. Years after the encounter, the solar system exhibits a new equilibrium. Orbits stabilize, debris fields thin, radiation levels decline. Earth's environment, though transformed, supports pockets of enduring ecosystems. Adaptation becomes the defining narrative of survival. The observation station transitions from emergency monitoring to long-term research. Its archives become humanity's most valuable scientific record. Through catastrophe, knowledge expanded beyond imagination. But the universe remains vast and silent. The rogue black hole continues its journey beyond detection, carrying with it fragments of worlds it reshaped. Its passage leaves behind a question that will echo through generations. Was this event rare, or was simply the first humanity has witnessed? Scientific understanding advances rapidly as data from the event reshapes fundamental theories. Gravity is no longer perceived solely as a predictable force, but as a dynamic architect of cosmic evolution. Researchers reconstruct the sequence of planetary deformation, tidal heating, and orbital migration with precision never before possible. The solar system itself becomes a living model of gravitational interaction. Education, exploration, and observation all evolve in response. Humanity's view of its place in the universe expands beyond permanence toward participation in cosmic change. And in observatories across Earth and orbit, telescopes scan the darkness, searching not for threats alone, but for understanding. Cultural impact spreads as profoundly as scientific discovery. The event reshapes philosophy, art, and humanity's perception of cosmic vulnerability. Images of warped skies, luminous debris rings, and transformed Earth become symbols of resilience and impermanence. The solar system is no longer a static home. It is a dynamic environment shaped by forces beyond prediction. Yet survival demonstrates an equally powerful truth. Stability can emerge from disruption. The memory of the rogue black hole becomes part of collective human identity, a reminder of both fragility and endurance. Long-range telescopes continue to track gravitational signatures across nearby space. Though the rogue black hole has departed, its path remains measurable through subtle distortions in distant starlight. These observations allow scientists to map its journey through the galaxy. A traveler recorded not by light, but by influence. The solar system's transformation becomes a reference point for future encounters. Preparedness replaces uncertainty. Humanity now understands that cosmic events once thought unimaginable can unfold within observable timescales. In reflection, scientists recognize that the solar system did not merely survive, it evolved. New orbital relationships, new geological conditions, and new knowledge define its future. The encounter demonstrated that cosmic destruction and creation are inseparable processes. Worlds can be reshaped without vanishing. Systems can endure transformation. From orbit, Earth shines, scarred yet present, beneath a sky forever changed. The universe continues its silent motion, vast and indifferent. But humanity now watches with deeper understanding. The rogue black hole is gone, its presence detectable only in memory, data, and transformation. The solar system endures as living evidence of gravitational power, a system once stable, now evolved. Earth continues its journey around the sun along a path rewritten by cosmic encounter. Its atmosphere thinner, its oceans altered, yet its existence sustained. From orbit, observers watch a familiar yet transformed world rotating beneath them. In the silence of space, one truth remains. The universe is not static. It is an ever-changing tapestry shaped by motion, gravity, and time. And somewhere in the vast darkness beyond, other travelers move unseen. The story does not end with survival. It begins with understanding.